In this video, we will start examining fluid dynamics in a rotating frame of reference. We do this so as to better understand the large-scale geophysical flows of the atmosphere and the oceans, which we experience in the rotating reference frame that is provided by Earth. We begin by performing a reference frame transformation. Up to now, the focus of the course has been on understanding fluid flows in an inertial reference frame, where fluid motions are driven by pressure gradients and gravity. You've become familiar with the continuity equation for incompressible fluids and the Navier-Stokes momentum equation, which for inviscid flows reduces to Euler's equations in three directions, where the horizontal accelerations are simply functions of their respective pressure gradients, and the vertical equation maintains a gravitational component. These equations are in an inertial reference frame, meaning the reference frame is homogeneous, isotropic, and time independent. Now, planets rotate, and thus they do not provide an inertial reference frame. So far, we have been able to overlook the fact that Earth is rotating because the flows that we have been interested in have time scales that are much smaller than the planetary rotation timescale. It is not always the case that background rotation can be ignored. To describe these flows with sensible equations, we need to first perform a bit of vector calculus to recast the equations of fluid motion into a rotating frame of reference. Consider the vector x in a fixed frame of reference, Rf, with some arbitrary origin O. This origin can be arbitrary because Rf is an inertial frame of reference. Now consider a second reference frame, Rr. This one is rotating about some axis that coincides with our arbitrarily located origin O. The rotation rate about this axis is omega. Now the vector x is composed of two vectors relevant to this new frame of reference. X is composed of an along-axis component, z, and an off-axis component, r, which is also the radial distance from the axis of rotation. This decomposition of x into its along-axis and off-axis terms introduces a new vector cross product, omega cross x, which is orthogonal to both the radius r and the axis of rotation omega. To relate the two frames of reference, one fixed and one rotating, it is best to consider their movements relative to one another. For a vector x, this becomes two velocities, the rate of change of x in the fixed frame, uf, and the rotating frame, ur, so that for any vector x, the transform between the fixed and rotating frames is given in terms of this vector cross product, omega cross x, and the rates of change of x in the two reference frames, remembering that one frame is moving relative to the other, so that these velocities cannot be identically zero simultaneously, except in the case of the null solution, where omega or x are zero. For fluids, we are often interested in accelerations, so it is convenient to perform this transform on the vector describing the fluid velocity in the fixed frame, uf. We know that uf is related to the velocity in the rotating frame, ur, by this equation, so we can make the substitution for uf on the right-hand side in terms of the derivatives in the rotating frame, giving us the velocity in the rotating frame plus the term omega cross x. We separate this out to get the acceleration in the rotating frame, the rate of change of omega cross x in the rotating frame, the cross product of omega, and the velocity in the rotating frame, and this triple vector cross product, omega cross x. Now, omega is invariant in time, meaning the time derivative here only applies to x, giving us a second omega cross ur. Let's pause here for a moment. We have the acceleration in the fixed frame equal to the acceleration in the rotating frame plus two additional terms, 2 omega cross ur,
which is called the Coriolis term, and this triple vector cross product omega cross x, which is often called the centripetal term. At this stage, we substitute this transform back into the Navier-Stokes momentum equation in a fixed frame of reference, giving us the total time derivative in the rotating frame plus the Coriolis and centripetal terms as equal to the gravity, pressure gradients, and viscosity terms.